All right, so we're going to be talking about the fundamentals of Cartesian coordinate systems and the various different things that we need to pay attention to when we're using this in the Atmosphere Programming CAM CNC product. So basically we want to talk about the first thing. The primary axis of the Cartesian coordinate system is your x-axis. Now, according to Cartesian, as you're looking down on the plane, the axis that is to your right is your primary axis. And so when we're looking at a plane from straight down, x is our primary, y is our secondary axis, and z is our tertiary axis. Now, there are other aspects of G code, the CNC code, that we need to be paying attention to as well, and that is, for instance, the primary tool vector. Well, the primary tool vector is going to be the I, or the x component of that vector. And we'll talk about vectors in just a few moments. The secondary tool vector is a j value, and that is relative to the y component of the vector. The tertiary vector is the k value, and that's relative to the z component. Now, interestingly, in G code, the I, j, and k are also used as the primary, secondary, and tertiary arc centers when we're working with a G2 or a G3 arc record. Now, the I again references the x value, the j references the y value, and the k again references the z value. Okay, and very important too is when we go to the rotary axes, standard Cartesian alignment puts the a-axis rotary or the a rotary, I should say, rotates about the x-axis. The B rotary rotates around the y-axis. And of course the C rotary would then rotate about the z-axis. Now in many of the CNC machine tools on the market, you're going to see that alignment very standardized. In some of the machines on the market, they may not use those letters. For instance, in a Haas, the A-axis is your tilting axis, the B-axis is your rotary axis. They don't worry about C. So it doesn't matter whether your tilt rotates around the x-axis or rotates around the y-axis, Haas still calls that the A rotary, okay? So let's go ahead and go on into the next level of this, and let's talk about one of the standardized rules of the Cartesian system is mapping the angles of rotation. And as we said earlier, the primary axis of the XY plane is, of course, the x-axis, which would be your 0-degree orientation for a circle. And you go to the y-axis positive, and that's going to be your 90 degrees. And of course, the negative x-axis becomes your 180 degrees. The negative y becomes the 270 degrees. All right? That makes up your primary plane, or what is known as the G17 plane in G code. Now, quadrant 1 of the G17 plane is right here. Many people believe that it's there because it's positive x and positive y coordinates, and that's not actually the reason why. You see, Cartesian has what they call a rule of rotation. The idea being that you stand at the positive end of the vector, you look towards the origin, and a counterclockwise movement of the tool about the axis of rotation is a positive angle of rotation. And so the quadrant 1, Q1 being in the x positive, y positive, is simply because that's the first quadrant of rotation around the origin. Now, when we look at the secondary plane, the primary plane being made up of the primary axis and secondary axis, the secondary plane can have two definitions. I'm going to talk about the first definition, and then I'll cover the alternates in just a moment. Most of the machines in the CNC world, the G18 plane, or what a lot of people refer to as the XZ plane, is made up of the x-axis and the z-axis. So your primary plane being made up of the x and the y, secondary plane being made up of the x and the z. The thought process is, for the first plane, of course, you would use your first and secondary axes. In the secondary plane, you would use your first or primary axis and your tertiary or third axis. If we follow the rule of Cartesian by standing at the positive end of the cardinal vector, and looking towards the origin, then we would be, in order to view this plane, we would be standing at the positive y end of the y-axis, looking towards the origin, and what we would be seeing is x negative on our right-hand side. And so therefore the true nomenclature for this plane, for the G18 plane, would be the negative xz plane. The only reason that that's kind of critical is because when we're talking to people over the phone or through media that doesn't put us in the same room with each other, sometimes it can be confusing if somebody's calling it the xz plane, but we're actually looking at it from the other side of the machine, from the back of the machine. From the operator view, looking towards the table, if you were in the front of the machine looking to the back, you would be seeing the xz plane. But that's not necessarily the G18 plane. The G18 plane, you would want to go around to the back side of the machine, look forward to the machine, and you would be seeing the negative xz, and that's the actual plane designation. Now, the tertiary plane in this particular alignment would become the YZ plane. So again, we would stand at the positive end of the cardinal axis, the x-axis, looking towards the origin. The axis to our right would be the y, and the axis up would be the z. That would be referencing us to the G19 plane. Now, I've talked a little bit about alternate orientations. I have run across a few machines in my career that alternate orientation was what the machine was using, and the G18 plane was actually the YZ plane. The G19 plane was the negative XZ. Now, the school of thought on this, from the people that I heard it from, was that to witness the primary plane, you use the primary axis and the secondary axis to define the plane. But to see the secondary plane, you would go stand at the end of the primary axis, look to the origin. The plane that you see is your secondary plane. Then you would move to the positive end of the y-axis, or your secondary axis, look to the origin, and the plane that you would see would be your tertiary plane. Now, both of those are acceptable arguments, and the people that believe one way are fixed in that because that's what they were taught. I don't really look at this as a right and wrong way of looking at it. I want to understand what the machine is doing. So the lion's shares of CNC machines in the market today will be using this first orientation that I talked about, where the G18 plane is the negative XZ plane. But there are a few machines out there, I've run into them from time to time, where G18 is actually the YZ plane. It simply helps to understand this so that we know what we're dealing with when we're trying to write the post-processor, okay? So now, as we go on, this is another one that kind of turns everybody upside down sometimes. This is the turning axes. Well, when we start looking at the Cartesian alignment in a turning center, a standard lathe, the z-axis positive is to your right when you're standing at the controller of the machine. And your x-axis is either to the back of the machine on an angle upwards, or in some cases straight up. And the y-axis would be coming either from the top of the machine or out towards the operator. So this is actually a different plane. This is the ZX plane, not the XZ or negative XZ. Z being the primary axis in this orientation. So it's kind of critical to be able to understand these nomenclatures and decide how we're looking at the machine by those designations. Now, as we look at the definition of a vector, a lot of people have a lot of different ways of describing a vector. In the CAM systems, we use what's called a unitized vector. This is a one-unit line segment with its origin at 0, 0, 0, and its endpoint at some XYZ coordinate 1 unit away from the origin. Now, the reason I say 1 unit is we really don't care whether it's 1 inch, 1 millimeter, 1 meter, 1 mile, 1 foot. It doesn't matter, it's 1. The reason it's 1 is because that makes the rest of the trigonometry very easy. The hypotenuse of your triangle is 1 unit. All of the other math in the triangulation becomes significantly easier to work with when 1 is our base. The reason I talk about that is because in the CAM system, most CAM systems use a 12 register matrix to identify the orientation and the position of the coordinate work system. The first row of this matrix is identifying the x vector. Now, if we always follow a rule where we never state the axes out of order, x is the primary, y is the secondary, z is the tertiary, so we always say them in that order, x, y, then z, it means that we don't have to declare the axes when we're talking about a vector. We can talk about the x vector as being one unit along the x-axis from the origin. It's parallel to the x-axis. We can state that vector definition as 1, 0, 0, because if it's perfectly parallel to the x-axis, then it has not moved from the origin on the y or the z. And when we move to the z vector, or the y vector, excuse me, in the second row down in the matrix, we're going to notice that if that's one unit and it's parallel to the y-axis, then it's on x0 and it's on z0, so that becomes a 0, 1, 0 vector. Going forward to the z-axis, that becomes a 0, 0, 1 vector. So it's very easy to describe a coordinate orientation and position by simply stating the three vectors and the origin position. 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0 identifies the world coordinate system as we use it in CAM. Now, as we go forward and we start looking at an orientation that is not the world orientation, where we want to actually look at the work coordinate system in the machine, then we need to reference what we call an MCS, or a machine coordinate system, relative to the world coordinate system. Now, to help with this, let me bring up a couple of files here that I think will add a little flavor to this. I'm going to start with a AC rotary system. We'll talk about rotaries here in just a moment. This particular block gives us a way of looking at how things work. Now, I'll be using a 3D Connections 3D mouse to rotate this around. Makes it much easier to work with the model here on the screen. But notice this center coordinate system in the middle of this 4x4x4 cube has a circular origin indicator, versus all the rest of these have a cube at the origin. This is world coordinate system here at the center of the box. These are all representing machine coordinate systems. Now, I want to think about something when we start talking about machine kinematics, okay? Taking a look at this block in this position, world coordinate system is looking like this, okay? As if we were looking down on this from the top, we would be seeing it in this orientation: x to my right, y up, z towards me, okay? If I want to work on this face over here, depending on the machine I'm using, I've got to get that face up to the top to align it with the tools. To do that, we have a couple of different options. If I'm working in a 3-axis machine, I'm going to have to pull it out of the vise, turn it around, put it back in the vise, and then identify how I've aligned it to the CAM system. But if I'm working with a machine like we have here, the Hermle C42, this has a rotary table system, what we call a trunnion table, and it allows us to actually rotate the block programmatically. And so, as we're thinking about this, this is an AC rotary, meaning that the tilt axis rotates around X and the rotary axis rotates around Z. So it would not be possible for me to do a straight rotation and roll this block up to the top. That's not a physical possibility on this machine. So how would we have to do it on this machine? Well, there's two solutions. We can first rotate positive 90 on the C-axis and then rotate positive 90 on the X-axis, bringing that face to the top in alignment with the axis of the tools, and we could do machining on this face. Now that's an an AC orientation. Let me go ahead and close this file, and I'm going to bring in another file. And this is what we would consider a BC alignment. Okay, working with a rotary orientation where the B-axis is the tilt axis around the Y-axis of the coordinate system. So if I'm working on this same face over here, in this case, I can simply rotate the tilt axis and bring this tool up to the top. Now, again, as we follow that Cartesian rule, if we're thinking about tool motion the entire time, the Cartesian rule is stand at the positive end of the vector, look to the origin. A counterclockwise motion of the tool would represent a positive angle of rotation. So in this particular case, if we were to do that, if we rotate, if we were standing at the back of it, okay, back here on the back, look, positive Y looking forward, then rotating the actual table this way would rotate the tool counterclockwise, looking at it from the back. And so again, this is a positive 90 rotation angle. Okay, so I hope that brings a little bit of clarity to how we manage those axes of rotation. Now let's go back to the document for a moment. And let's take a look then at how that works. Let's rethink our minds back to that AC alignment. And if we were trying to build the machine work coordinate system for this alignment here, we're going to take the x-axis and reference it to world. So the x-axis is parallel to the world y, which would make it a 0, 1, 0 orientation. The y-axis of machine coordinate system is parallel to the z-axis of the world coordinate system. So that makes that a 0, 0, 1 designation. The z-axis of the machine coordinate system is parallel with the x-axis of the world coordinate system, making it a 1, 0, 0 vector alignment. Now, because the origin of this coordinate system is out on the face of the box instead of being at the center of it, and we said this is a 4 by 4 by 4 cube, that means that the position for the origin would be referenced as 2, 0, 0. This gives us a 12 register matrix that the CAM system can then use to transform model coordinates into machine envelope and coordinates. That's why this is important, and this is why at least a conceptual understanding of how these work is pretty critical. We don't need to necessarily know how to work the transformation matrix math, but it helps significantly to understand the orientation and the position of the coordinate system that we're going to be using to do our machining. Okay? Now, going back to the BC, notice that this coordinate system, the same face, but the machine coordinate system takes on a completely different alignment. It's now a 0, 0, negative 1 for the X machine coordinate system, a 0, 1, 0 still for the Y-axis, and a 1, 0, 0 for the Z-axis. So that's critical in understanding how you want to set up the alignment of your coordinate system. Now, in most engineering classes around the world, they teach what they call the right-hand rule. In the right-hand rule, this is your x-axis, this is your y-axis, this is your z-axis. The curl of your fingers represent the positive angle of rotation of the tool around the z-axis. But that's kind of a limited functionality, and quite honestly, it's uncomfortable to hold my hand like this, and it kind of looks like I'm flipping you off. So I really don't like to use that. I like to use the left hand. We can do the same thing. Now, let's take a look over here at the machine, and I'll show you what I'm talking about. If I walk up to any vertical CNC control center, and I stick my hand in the open doors like this, my middle finger is pointing to the direction of positive X tool motion. My index finger is pointing to the direction in the machine of positive Y tool motion. and my thumb is pointing to the direction of positive Z tool motion. That makes this very easy to understand. Regardless of whether the table moves or the tool moves, I'm pointing to the positive directions of the tool motion, even if it's in reference to the table motion. Now, we always see in the control systems, like you see on the picture on the screen right now, the isometric orientation of the view in the CAM system is always in the fourth quadrant, elevated above the plane, looking at the system that way. Now why? If we really think about it, there's an infinite number of, quote, isometric views. We could be looking at it from quadrant 2, 3, or 4, above or below the plane, at any angle into the plane and any angle departing from the plane. So there's really an infinite number of isometric views that could be legitimate. Why do we use this one in virtually every CAM system I've ever seen? Well, it's a simple answer. In almost every machine on the planet, unless this controller is on a pendant or it's just a weird machine where they put it on the left, the controller is always right here. And so what is the user used to seeing when they're standing at the control programming the program? They're looking at the part from the fourth quadrant, elevated above the plane. And so that's a system that is very comfortable and very common for most machinists, and that's why we use this particular orientation as our standard isometric view. Okay? So let's go back to the document and carry on from here. The beauty of using this left-hand configuration system is that it gives us the ability to use our other hand as a tool as well. If I take the thumb of my right hand and I map that parallel to the positive direction of the axis of rotation, the curl of my fingers around that axis, in this case the A axis around the X, is the positive or counterclockwise direction of the tool, even if it is the table that rotates. If the tool rotates like on an articulating head, that's simple. If the table rotates, it's going to go the opposite direction so that the tool goes counterclockwise. And I have a reference for my A axis, my B axis, and my C axis. Now this makes it very simple for me to walk up to a machine like this, and let's go over here and take a look at this again. We're going to take a look at the rotary. You got the jog? Yep. Kevin's going to help me out a little bit here with it. And we're going to jog this table. Now I'm going to get out of the way so we can see this table. But we're going to take this and we're going to move a positive A-axis motion. Go ahead and let's look inside the controller here. We can see the table moving, right? Now, stop it. What happened there? The table is moving clockwise, which means the tool is moving counterclockwise, okay? Now, if I had walked up to this machine, and give me a negative, if I came from my neutral position and I rolled it positive and it went this way instead, then we can notice that that would actually create an anti-Cartesian alignment. That doesn't mean the machine's wrong. It just means I don't have a Cartesian alignment. I have an anti-Cartesian alignment. I can manage that in the post very effectively. So I need to know what that's going to do. Let's go ahead and bring her back to A0. Now we look at the C-axis rotary on this. Once we get back to A0, we're going to do a positive C motion. So let's see a positive C rotation of the table. Notice the table from looking down is going clockwise because the tool is stationary. That means we are seeing a proper Cartesian counterclockwise movement of the tool, even though the table is what's moving, okay? So we know that's a proper Cartesian alignment, not an anti-Cartesian alignment. And that helps us understand verbally what it is we're dealing with this particular machine and how we need to write our post to be able to get G-code from the CAM system into this controller in a way that it'll run this machine effectively. Now, as we talk about reference frames, okay, there are many different ways to look at how we're working with a machine and how that machine is oriented or setting in the real world, okay? As we talk about our world reference frame, the coordinate system's alignments must reference back to some sort of a world orientation and alignment of that coordinate system, okay? There's also an operator's fixed frame coordinate system, which would of course then be relative to the WCS or the world coordinate system for the machine position and orientation. There may also be a machine fixed frame coordinate system, like for instance in a horizontal, you know, this vertical machine has this alignment. Most of the horizontals have this mechanical alignment. The operator view is still the same, but the machine kinematic alignment is completely different, okay? And so we want to keep that in mind as we're looking at all these different functions and recognizing and understanding how this machine is stood on the floor and how the operator relates to this machine. And as we think about these fixed frames and where the operator perspective is, it helps us to understand the part alignment in the machine as well. So I want to talk about some different ways of identifying this. Sometimes we'll put a sub-notation on the axis, X prime 1, Y prime, Z prime. Okay, that can give us an idea that that's the first referenced axis, and we may reference a secondary axis in a different orientation. Now, in a vertical, as we're looking at this on the screen, in a vertical machine alignment, it's interesting that the machine kinematic alignment is actually parallel to the machine's operator perspective, right? But as we go into a horizontal machine, notice that if you're standing at the controller as the operator, your perspective is still relative to the machine world coordinate system, but it is not the same as the machine kinematic alignment. And so we need to understand that in order to be able to set perspectives of view correctly in the system, all right? So we can designate those as X prime 2, if you will, Y prime 2, Z prime 2. Now, another thing that we need to get into and talk about is the offhand coordinate system. Now, a lot of different machines in the world have all kinds of different crazy coordinate system alignments. Depending on the manufacturer of the machine and depending on what the sub-machine function is, it may move differently from one maker to another on how that's supposed to work. Now, we have an offhand alignment as well. There's a lot of different things that happen on machines, and we have to take care of those. On a Swiss machine, for instance, you can have two gangs of tools that either work in unison with each other, work independent from each other, and can have any of various different alignments with the machine kinematic for functionality. And so sometimes we have to use the other hand, and let me help you understand how that works. To do that, let's walk over here to the lathe and we'll take a look at how a lathe works. Now, in this lathe, and you're going to want to pan back and forth from time to time. Huh?
You're good to jog.
Good to jog, okay. In this lathe, we have the main spindle here and the turret body here. The coordinate system for our machining in here, this is the x-axis that runs up here. This is the z-axis that comes across here. So your thumb follows the z, this finger follows the alignment of the x, and that puts the y-axis coming out this way if a y-axis existed on this machine. That's a different alignment, isn't it? That's not the xz, it's the zx. It's a different alignment of the coordinate system, and we have to be aware of that. Now, if this were a Swiss controlled machine, there would be gangs of tools here that work on this main spindle. And if the front gang of tools works independently from the rear gang of tools, the front gang would have this orientation with X positive coming away from the spindle, Y coming up, and Z going positive this direction. Again, tool motion, excuse me. The back gang would actually have this alignment. X positive going away from the machine, or away from the center line, Y coming up, and Z going out this way. So that puts them in this alignment and helps us understand exactly how those subcomponents move in that machine. Now, machines that have multiple turrets, sub-spindles, and different arrays within here of gang tools and such could have any number of different alignments. In some cases, the front gang here has this alignment because they consider the part movement going this way to be positive. And that's how that machine's programmed. There's nothing wrong with that, but boy, it helps to understand it. Now, on some of those machines, the back gang actually works independent from the front gang and therefore has this alignment unless it is linked with the Z1 axis, where then it has this alignment. And so it gets crazy, all right? So it really helps to understand, as we're looking at a turret like this, what are the turret coordinate systems for each of these pockets? And we can mount those in however they're oriented by the machine tool manufacturer in the VMID of our post-processor, and give our software the opportunity to move this machine according to the way the manufacturer set it up. All right, so now let's start talking a little bit about another interesting phenomenon that takes place with CNC machines. We have fixed frame rotations and linear movement, and we also have floating frame relationships, and I want to talk a little bit about that. A linear floating frame would be another alignment that can be moved along the axis of another subsystem. So if I've got these two systems up here working, and maybe this back one has a B axis, that B axis could float like this, but it probably moves along the primary fixed frame axis of the X or the Y, okay? And so as we go through this document a little bit, I cover a lot of information in here, and I can make this document available to anybody, of a linear floating frame axis and a rotary floating frame axis. Now, what do I mean by that? If I take an axis, let's say my primary rotation is going to be over my X-axis. So I rotate that function, right? So this was a fixed frame rotation. The fixed Y frame is here. The fixed Z frame is here. This is a floated frame of alignment here. If my second axis rotates here, that would be a floating frame rotation. If my first fixed frame rotation was then followed by a secondary fixed frame rotation, that is a completely different alignment. And it's one that we have to pay attention to and make sure that we understand the kinematic functionality of that rotation. Was it a fixed frame, float frame, followed by a float frame? Or was it a fixed frame, fixed frame, fixed frame? Those are all different math equations, okay? Again, we don't need to know exactly how to work the math, because that's what the computer does. It's what the software does for us. It really helps to understand this conceptually. It really helps to understand this conceptually. So let's think about a situation where we might use that in the real world. Most of you have seen, heard of, in many cases used, compound sign plates. A sign plate is something that we can raise up, set on a Joe block, and we can calculate the angle that that is creating. A compound sign plate has two hinges. This can move and this can move. Now, the order that you put those hinges in can determine everything about what those movements are. If my Y rotation is here, my X rotation is here, then if I do this and this, I have that angle. If I reverse those, right, and I do this and this, those are totally different angles. And they don't line up the same. So we need to know the order in which the rotation occurs and whether or not it is a fixed frame rotation or a floating frame rotation in order for the software to position tools within 1/10,000th of an inch. okay? And so as we begin to look at a machine that has this kind of capability, as you can see in this picture on the screen, this can get very, very complex. We can have situations like we've got here, where we've got a normal Cartesian coordinate system, and then on the front gang, we've got an offhand coordinate system. We have a turret that drives along an X3, Y3, and Z3 tertiary series of axes, and also has a B-axis component aligned with it that can allow us to articulate away from cardinal axis functionality. So that creates a system where if we're trying to track the tip of that tool through Z3, X3, Y3, B3 rotation, all of those cosine offsets that happen in there have to be tracked in order for this tool tip to now still meet that part where it's supposed to meet that part, okay? And then we have other components back here. We've got a C2 that has an X2 and a Z2. We have, of course, all the X1, Y1, Z1, C1 functionality. All of those things can be programmed simultaneously. When we start talking about Swiss machines, we can get into multiple axes of orientation. We can get into, I have seen as many as 19 axes of motion with up to 5 axes of simultaneous motion. Now, I have heard of, so far I haven't been in front of one, but I've heard of other machines that have multiple spindles, have up to 4 different turrets, and even B-axis on both an upper turret and a lower turret, where the machine can actually drive in 5 axes simultaneous on one submachine while it's driving 5 axes simultaneous on the other submachine, giving us 2 stations of 5 axis simultaneous motion. And then you start counting up all of the other sub-axes that run with the other 2 turrets, and it's pretty easy to accumulate 19 axes of motion. It's not so easy to program 19 axes of motion, but SolidCAM can do it. Okay, so that kind of concludes what I wanted to talk about today. Thank you for being a part of this. I hope you got some fun out of that.